Number 7. A shopper pushes a grocery cart 20 meters at constant speed on level ground against a 35 Newton frictional force. He pushes in a direction 25 degrees below the horizontal. Letter A. What is the work done on the cart by friction? All right. So why don't we first just try to set up a free body diagram? All right. I have the picture detailed over here, right? And so let's first try the free body diagram with this. So what I'm going to do is I'm basically going to detail this point right here as the origin for my axes. All right. So now if I do that, okay, it tells us that the guy or woman, whoever it is, he. So the guy, he pushes the cart, right, at an angle 25 degrees below the horizontal. Okay, so that means he's pushing the cart down this way, right, and right here is the 25-degree angle. So in my free body diagram, let's draw that. All right, we'll draw a vector that way. This is the force that he is applying. We'll call it FA. And the angle they told us was 25 degrees below the horizontal. So that's 25 in there. Okay. All right, great. And then what other force does it tell us is going on here? It also tells us that there is a frictional force, right? It says 35 newtons of friction. So where does friction point in the problem? Remember, friction always opposes the motion. So in my picture here, I'm assuming the cart is moving to the right. Therefore, friction would oppose that, right? It would point directly to the left. Okay, so this is the frictional force over here. And it told us the value 35 newtons. So 35.0, right, newtons. Okay, so let's see now before I answer any questions, you know what? Let me just start breaking this up into, right, X and Y components and all that stuff. All right. So why don't we just break this vector up into X and Y components to start with? All right. So let's draw the X here. Right. We'll call this FAX. Okay. And then this will be FAY. Right. FAY. All right. So how do we find the X component? Well, we know the hypotenuse, right? We know this angle, and we're looking for the side adjacent. Therefore, we're going to use cosine. Right? So cosine of 25 is equal to the adjacent side, which is FAX, all over FA. Okay? Cool. So now, solving for the X component, right, it would simply be a cross multiplication. So FAX will equal FA times cosine of 25. All right, let's put that in a little box. Now, let's do it for FAY, all right? So I know the hypotenuse, I know this angle, I'm looking for the side opposite, therefore it is sine. So sine then of 25 will equal the opposite side, or FAY. I'm going to plug in the negative here because it is in the negative y direction, and divided by the hypotenuse, which is FA. Therefore, cross multiplying and then distributing the negative sign, right, we should get FAY is equal to negative FA sine of 25. Well, let's pull a box around that. Okay. Now, what else does it tell us in the problem? So it actually, well, you know what? Let me not jump because now I'll probably be jumping ahead. So let's just focus on A now. So let's say, what is the work done on the cart by friction? All right. So for letter A, right, if we're looking for work and we're talking about friction, okay, we're probably going to be referring to this formula over here on the right. All right. Now that says the work done on an object is equal to the force that is applied to the object multiplied by the distance that object travels, multiplied then by the cosine of the angle between the force vector and the distance vector. So I'm looking for the work done by friction. Therefore, I have to think about the force of friction, right? And then the distance the object travels. So the work of friction is equal to the force due to friction. Remember that was 35. Do not plug in the negative sign here. You'll see where the negative sign or how the negative sign comes about in this problem. So 35. The distance that the cart is traveling, right? The distance it traveled was 20 meters, they told us. Okay, 20 meters. And then cosine now, what's the angle between these two vectors, right? If you think about it, the force of friction here is going back this way, right? It's opposing the motion. But the distance vector, right, or displacement vector, I should say more properly, is pointing to the right. So what's the angle between those two lines? 180. Okay, so when you plug in 180 over here, guess what cosine of 180 is? -1. There's where the negative comes from. All right. So now, 35 times 20, 700. Okay, and negative, right? So negative 700 joules. Okay. So that's the work. All right. Let's take a look of friction, that is. So let's take a look at letter B. So what is the work done on the cart by the gravitational force? Interesting. So for part B here, I think we can simply answer this. All right, part B. So take a look at my free body diagram, guys. Is gravity even really acting in the problem? You might say, well, wait a minute. Yeah, I mean, there is a frictional force, right? So there should be a normal force of some sort. And the normal force would come about due to gravity. So, I mean, yeah, but we don't know the mass of the object, right? So we would be hard pressed to, nor do we know the coefficient of friction here. So we wouldn't be expected to find that. However, though, if you do look at my free body, excuse me, if you do look at my free body diagram, there is no gravitational component to it down here, right? It's not moving, nor is it in free fall or anything like that. There's no, there is no gravity component to it. Okay, the motion is in the pure x direction. Okay, so that's the direction I'm concerned about. All right, things going on in the x direction. So what is the work done on the cart by the gravitational force? 0. Okay, cool. And if you wanted to even understand that more intuitively, meaning in terms of the formula, okay, even if we were to know the mass, right, and of the object, and then therefore multiply it by 9.8, and we knew the distance it traveled, what's the angle between the distance here and gravity? Well, it would be 90 degrees. Guess what cosine of 90 is? 0. So if that's 0, this whole thing goes to 0. All right, that's another way to look at it. Anyway, let's move on. So letter C. What is the work done on the cart by the shopper? All right, so letter C, let's put it over here. And now, well, how do we relate work to force and all that? It's going to be the same equation, right? So let's write down here, so the work done by the shopper will equal to the force applied by the shopper, multiplied by that distance the cart travels, multiplied then by the cosine of the angle between the force vector and the distance it travels. Okay, so somehow I have to, in order to find the work done by the shopper, I got to know all these things. Now, what's the big problem? I don't know what this is at the moment. So my focus turns into, instead of finding the work the shopper applies, my job really is to find the force that the shopper is applying to the cart. Now you look at the triangle right over here in your free body diagram, and we realize, though, the only other piece of information we know here is the force of friction. So how does the force of friction connect to any one of these three vectors? How does it connect? Well, this is a pure x component, so it should connect to this somehow, right? That pure x component. Okay, well, how does it connect? Well, remember, we know that formula, the lovely one. Sum of the forces in the x direction is equal to max. And that x, right? The acceleration in the x direction. Well, what is the acceleration in the x direction? Well, look, guys, the velocity is constant, and the velocity is in the x direction. So if the x direction of velocity is constant, what is the acceleration? Zippo. So what happens to this whole side? Goes bye-bye. So the sum of the forces in the x direction equals 0. Now, what are the sum of the forces in the x direction? What are the forces in the x direction? Well, we just said it's going to be force of friction and FAX. So we got the applied force in the x direction minus the force of friction will equal 0, right? And therefore, the force applied in the x direction should actually equal the force of friction. This all makes sense, right? So then therefore, the applied force in the x direction should equal 35, right? 0.0 newtons. Okay, now, where can we go from here? Well, realize that now I know this part of my triangle. All right, so I can easily do some SOHCAHTOA, right, to get the hypotenuse. Now, I already solved something over here, but probably shouldn't have even wasted the time before necessarily, because I should have solved it for FA instead of FAX. I mean, it's fine. What we did is not a problem. It's just not really necessary. All right. So instead, let's solve this thing. Instead of solving it for FAX, let's solve it for FA. Right. All we have to do is switch the numerator and the denominator there. Okay. So FA will equal FAX divided by cosine of 25. So this is simply the force applied will equal FAX, right, which was 35, right, 35, all divided by cosine of 25. Let's leave it like this for now. Now we can plug this result, okay, into this formula over here. So let's do it. So the work the shopper applies will be equal to 35 over the cosine of 25, okay, times the distance the car travels, which is 20 meters, multiplied by the cosine of the angle between FA, look over here, FA, right, and the distance. So remember, FA is down this way, the distance is over this way, and it's really getting messy, right? I should have actually brought it up a little bit. Here's the distance, here's FA, the angle's 25. So notice what actually happens to these values, these cosines. What happens to them? Goodbye. Right, they're done. And that should make sense, right? Because the work the shopper is applying, right? It's the distance is the distance the car is traveling is in the pure x direction. Therefore, I'm really only concerned about the pure x component. All right, and so that actually works out nicely. So we get 35, right, times 20, so it should be 700 again. Okay, interesting, right? Same result as I got over here. There's no net force on the cart, right? There's no acceleration on the cart, so there's no net force. So therefore, the work due to friction of negative 700 should have been equal but opposite to the work done by the shopper, which it worked out to be. So letter D, find the force the shopper exerts using energy considerations. So actually, we basically just did that, right? That would be this part right over here. All right, so if I were to solve this thing for now FA, meaning I just plug it into the calculator, I can easily solve that, right? So let me put down letter D down here on the corner, all right, bottom left. So simply, it's 35, right? 35 divided by cosine of 25. So what do we get? We get 38.6. So FA is 38.6, and that is joules. No, excuse me, newtons. Whoops, newtons. Got units all over the place here. All right, but that would be the applied force. And then letter E, what is the total work done on the cart? Well, remember, we just basically talked about that too. All right, let me put E up here. The total work done by everything, everything, the total work was what? 0. Negative 700 from friction, 700 from the work of the shopper, and 0 of gravity. So if you add all that up, right, X and Y components separately, it works out to 0. All right? So that takes care of that. And that's 0, well, that's 0 work, but I should say 0 joules, right? So there we go. Guys, thanks so much for tuning in. Hope this helped. Please remember to subscribe. And I look forward to seeing you in the next problem. Well, not seeing you, talking to you, or helping you, whatever you want to call it. Thank you so much.